stand by. All right. Well, and while that's taking place, all right, good. While that's taking place now, we can get back to this. The polar, with the example being water, if you're asked to show why is water able to conduct a current, why does water behave as if it is ionic? The reason for it, if we go back to the definition of an ion, you're going to say that what an ion is an atom that has either gain or lost electrons. Well, if water is polar, if we have hydrogen and oxygen bonding together, so it's one oxygen. In fact, oxygen is bigger, and maybe should show an image to explain this so that you might get a clearer understanding. All right. So let's look at the bonding in water and analyze it. Look at it carefully and see, because in electrolysis is very very likely. Water is one of those things that you know you're going to use in the exam, because if it's aqueous, then water is in there, and most of the compounds we electrolyze are aqueous. So let's have a look at water. Everybody seeing this?
Yes, sir.
Yes, sir.
All right. Now I hope you can make an understanding of this. All right. What is it that you're seeing? What you understand from the image on the screen? You see in three circles, and you have you have three letters there, and you have X and you have some dot. What do those mean?
There are two hydrogen atoms, one oxygen.
Very good. Start from the basics. All right. Two hydrogen atom, one oxygen. What else?
Are they bonding?
Yeah, they're bonding. Bonding. All right. Bonding how? How are the circles represented?
The circles represent two hydrogen.
We said that, but how are the circles represented? That's the question I'm asking. How they represented? Yes, it's three circles there. Are they consecutive? Are they intertwined? Are they separate?
So they
Yes,
intertwine.
intertwine.
Yeah, so use up your words, them. You express yourself, use up your word, them. So, all right. The correct word to use there, though, would be overlap. All right. So,
Okay.
part of one circle belongs to the other, or part of one circle is found in another, no so? All right.
Yes, sir.
Good. So that's it. That's the thing. So why is that so? Why do circles overlap when we're showing these diagrams? I'm not saying.
Sir, because they borrow the electrons.
Then borrow it. All right, I like that. So these are simple things, and they are the most obvious thing, because if you can't get the obvious simple things that are staring in front of you, how are you going to get the indirect things that CXE going to throw at you? CXE now go take it simple like how I do it, you don't know. You guys have to be confident, precise, and clear. You have to be clear. Not try to over explain. Or try to show people say you're bright or you know enough words. That's CXE one. CXE one know if you can answer the question when them ask you. Right? So and CXE don't know bright or dunce. That's not the purpose of grading. The purpose of them grading you is to see how well you answer the questions that them give you. That's it. So you can probably not know much chemistry and still get a grade one, because what? you answer the question them, right? And they can ask everything on the syllabus, so you can get away if you know the right things. They probably send a question, you get lucky in one exam, you answer the question the right way, you get a grade 1, bam, you're gone. All right. Nobody know if you know, say you don't know this or you don't know that. So focus on the question here. Focus on the obvious things in front of you. Right? Circles overlapping in bonding diagrams like this means that electrons are being shared. Everybody hear that?
Yes, sir.
Yes,
Yes,
sir.
sir.
All right. So when you look at a diagram, so this is the so this is showing. So diagram showing the covalent bonding in water. Covalent bonding is the sharing of electrons. How you show that in a diagram is right here. All right. So diagram showing
The 2 hydrogens, sir, and the 1 oxygen.
right covalent bonding in it's actually, yeah, so it's showing the covalent bonding. But when you get more experience, you wanna, well, let's look at it some more, because when you guys were learning ABC, it was just a letter A and knowing how to say it first before you could write it. And then now you can say it, now you can write it. And you get so good at it that if a child that's who is like 3-year-old try to write A, you can tell him, say, I know, say right. Right? Because you have mastered that. Now the same thing here. Details get more important to you, get more clear to you by looking at it over and over. So stepping it down. This is a basic thing that you need to understand, a basic diagram. But this diagram, again, it's what I like with chemistry. Diagrams are throughout chemistry and they're telling a story. This I can write possibly a 500-word essay on this little thing in front of me. Probably you can't do it, but that's where you need to be. I mean, that's where you should be looking to be. Picture is worth 1,000 words. So if I can only write 500, it means as a teacher, I have a lot to learn and develop with, but that's okay. You know? So diagram showing covalent bonding, right, in the water molecule. All right. From its name molecule, it means that the bonding is covalent. Everybody get that?
Yes,
Yes, sir.
All right. So you now go here we say sodium chloride molecule. No. Why?
Because it's a metal.
No, won't accept that. Sodium chloride is not a metal. Try again.
molecules are
What is sodium chloride? That's the question. What is sodium chloride?
sodium chloride.
Yes. What is the right term to describe sodium chloride as a substance? Is that simple? Is that simple 5-letter word? No.
Salt, sir.
Compound.
So salt have 5-letter now, January?
Solid,
Compound.
solid.
That's
Solid.
salt, sir.
No, man, no, there's no thing that. God, what's the opposite of covalent? What's the opposite of covalent compound?
Metallic. Covalent.
Ionic.
Ionic. No,
Sir,
no,
ionic.
Metal. Metal.
So, yeah, but on now come up with the answer. If it's not covalent, it's ionic. Think about that in terms of bonding, right? Forget about metallic bonding, because metallic bonding is just metals by themselves bonding, right? We are talking about compounds now where 2 or more atoms combine together to form one single substance, and that's called a compound. The compound can be either ionic or covalent. Right? And I've been saying this speech over and over. I almost sound like a recording. So I didn't even write it down because I've said it so many times and it just stick. Almost like a freestyle. So anyway, let me know. So if it's not covalent, it's ionic. By this stage, I expect say you're looking at certain compounds and you can tell me if it is ionic or covalent. All right. So when I said sodium chloride, yes, sodium is a metal, but chloride is there. So therefore, forget about the metal there. Sodium chloride is married now. It's sodium married to chlorine. So you have to respect that and call it what it is. It's an ionic compound. All right. So, think about it. So anyway, so this is the diagram showing what can be said of this diagram in front of you. So there's a covalent bond. All right. So water is covalently bonded. Is right, water, or you could say water has, well, so you could say the obvious, in 2 hydrogen atoms and 1 oxygen atom. All right, so that's it. That's the obvious there. Fine. Overlapping circles. All right, overlap. Actually, writing the word overlap. Overlap circles mean covalent bonding. So when you guys only take up book when class time come, now go work. All right, I only take off it. I mean, so we can move on because let's say sir now teach and then learn. But anyway, 3. So then we say the overlapping circles now means there's covalent bonding taking place. Why? What is the all right? So why we have red that different from blue cross?
For sure, the
because-
elements part
One at
hydrogen
a
different.
time. One at a time. One at a time. One at a time. Think I heard somebody else before you do Janari. So
Me.
Additional, sir.
Right. Go ahead, Chanel.
Sir, because the oxygen only have 6 electrons, so therefore, for it to be stable, you need 2 more electrons, but each hydrogen only have 1 electron, so that's why they're sharing it, sir. So the X represent the hydrogen, the electron for the hydrogen, which is sharing with the oxygen.
All right, everybody hear that? Everybody
Yes,
hear that?
sir.
All right,
Yes, sir.
Jenna, you still want to answer?
No, sir.
All right, class and Chanel, that was well said. Well
Thank
done,
you.
Chanel. So that is it, guys. I couldn't have said it better. All right. H, which is hydrogen, has only 1 electron. Everybody get that?
Yes, sir.
The X is representing the 1 electron of the hydrogen. All right. The other element that it bond with, they can't have the same symbol. We have to use something else. So that's why them call it dot and cross diagrams. When you're showing bonding, all right, overall in chemistry, you use a dot and cross approach, which shows that, which basically says that for one element, you use a dot, and for the other, you use a cross. All right. And the other rule is that if there's covalent bonding, then you should overlap the shells. So these circles actually represent shells. All right. So we can throw that word out of the, as a matter of fact, it's a special type of shell. So which shell is used for bonding in chemistry?
Valency shell.
That it again. Very fiery tonight. Yeah. All right. Hope everybody hearing that, right? The shells that take part in bonding are the valence shells. All right. So yeah. Everybody understand what we're doing so far?
Yes, sir.
All right. All right. So that's the valence shell here. All right. So me and covalent bonding, lovely. But grammar here, a little bit perhaps for many years not going to English class probably have this effect on you. Overlap circles mean covalent bonding is taking place. Or is occurring. That's right, occurring then. All right. So obvious things here. Yes, there's covalent bonding overlapping taking place. But then I wanted to also take another look at the diagram and see something else now. They are sharing. So the hydrogen is okay. Right here, hydrogen, this is shared. So this is shared, and then this is shared. Yeah, so that's sharing. So this part, notice that this part alone take part in the bond, you know. This part, you know, this is where the covalent bond take place, you know. And here, if I draw a little box around it, you're gonna realize something. All right, what is left outside the box that I've drawn? I draw the box to separate the two hydrogen and then part of the oxygen. What is left outside the box? Really? What is left outside the box?
4 electrons.
So when it takes so long to say that.
Sir, combinator if you're right.
No, well, no, common sense that. It's like me writing this and asking what is that? And writing this and asking what is that? From basic school. So where you can look at it, we draw a box around a part of the diagram and ask what left outside and nobody can tell me. Four little circle, 4 dot left outside. That mean electron. So therefore 4 electron leave outside. No man. I'm afraid and afraid. But me not biting no. I'm not afraid of. CXC bite hotter than me. Even if me bite. Anyway, between you and CXC. So 4 electrons are left outside the box, guys. That's where it all begins, guys. These are electrons. And remember, we talk about electrolysis, right? Electrolysis is using the electric current to separate. And then when you do that now, what happens is that the current pass through, yes, water get a piece of the current, but these electrons are on the outside of the bond. They are alone. They are left out there, right, to expose to the current. And so that is what makes it polar. That's what makes it, you know, sort of ionic, because electrons are kind of free there. No, so we use terms to describe the electrons in some, well, in a perfect covalent bond, there's what you call even sharing. And when you look at some molecules later on where there's an even sharing, like for example, if we have 2 hydrogen atoms bonding to form the hydrogen gas molecule, then that would be evenly shared. That you can't pass current through that. Those electrons are taken. And so when the current pass through now with the whole heap of energy now, you know that then they won't separate. They're just too happily married there. They're two are the same, you know, and so that happens. But then we have hydrogen and oxygen now. So, you know, even though oxygen has an 8, yes, oxygen now has an 8 share, but it's share, it's an uneven 8. It's like 2 of it, yes, it's share with hydrogen. So, you know, it's actually pulling those what this you see, and what oxygen does, because it's a bigger atom, it kind of bully hydrogen, pulls it in closer, right? And then has these electrons exposed to everything outside. So what I have here, so now these are electrons. And I'm going to end by saying that these electrons are polar. They are negatively charged. So when you have a negative charge there now, if up here so is negative, then what you find happening is this: the current not only just going to pass through up here, it will pass around it. So what's going to happen when the current pass around it? It's going to realize, it's going to feel like, say, all right, the current will go feel the negative up here. So, but when it pass through down here, so it will go feel the positive, because when hydrogen lose the electron now, four hydrogen only have the proton in the nucleus that's inside here. So we have is a plus and a minus situation. The parts where the electrons are is negative. The parts where no electrons are is positive. Hope you guys understanding that. In a covalent compound, when the electrons are not evenly shared, the part where the electrons are located is the negative side of the compound. Hope everybody is hearing that. Do you want me to repeat?
Yes, sir.
Yes, sir.
Yes, sir.
In a covalent compound, right, where electrons are unevenly shared, right, where electrons are unevenly shared, the part where the electrons are located in that compound is a negative part of the compound. So it functions as a negative part of the compound, right? Which means, and because we say it's unevenly shared now, we are saying that, okay, electrons are being shared, but not evenly. So it means that them are going there over one side more than the other. Everybody understand that?
Yes, sir.
Yeah. So when we take a look at this compound, we are seeing that all of the electrons, these X's here for the hydrogen and these dots for the oxygen, they are to one side of the compound. So it means if the whole electrons are one side, it means the opposite no. The opposite side of the compound does not have any electrons, and therefore it is going to be positively charged. Why? Because the protons them were inside the nucleus of the atom exposed is there. It is still there. It never went anywhere. The atom must have a proton and neutron, but then when it burns, nothing happens to the protons and the neutrons. They are still there. But what happens now is that the electrons now, because they have partially left now, it creates an imbalance behavior, an unbalanced behavior in the compound. Where the electrons decide to go, that part will be negatively charged, and the other part will be positively charged. And that's what polar means. Polar means that you have a north pole and you have a south pole, right? North is, well, I suppose when those persons who do physics will see more of this, but then just look at it this way. If the electrons there are closer to one side, then that's a north pole. I just call it a pole. And then if usually you don't have one pole, you have two poles. So then it works just like a magnet. So in fact, the reality is that water is magnetic. Right? They won't teach this at CXC level, but based on my exposure to the sciences and seeing how water behaves, water is actually magnetic. You can actually use a magnet to pull water, but then that's something for another class. The water has to be pure, however. It has to be pure. It can't have anything in there, not even little air can in the water. So that's a special type of pure water there. But water is magnetic. because the electrons in the molecules of water are located to one side. Remember, we said that it is a covalent compound, full stop. However, it's an unevenly distributed covalent compound. So it's an uneven covalent compound. And you know, electrons are found to one side, which means that the protons will be found to the other side. That makes it polar. Any questions here, guys?
No, sir.
All right. So that's a polar behavior, guys. No, this is just explaining how water now can be separated in that sense. And I wanted to, well, this diagram here. And here's the result now. I wanted to look at this diagram that I'm going to show you. Let's even duplicate this. So the end result is this. Slightly negative charge at the top, slightly positive charge below there. All right. And let me show you another image here. All right, let's duplicate this one now. Duplicate so I can show you something here. All right, and look at this one now. And so hopefully this will explain what's happening there. Everybody seeing this?
Yes, sir.
Yeah.
Yes,
Look at
sir.
my boo-boo.
What's that? All right. Electrons are pulled towards, yeah, the oxygen, definitely. And so that's what create that partial charge here. So water is polar. And from today's class, you should go away with that information. Water is polar. All right. So then I have to go ahead and draw that. Showed you already a while ago. But non-polar no. Other elements though, other compounds that are polar would be anything that has oxygen and hydrogen. Oxygen, we could say no, even hydrogen and chlorine. So HCl is one. That's polar. It's a covalent bond. However, chlorine, pull electrons more. In fact, chlorine and oxygen pull electrons in a similar way. Right? So that type of thing. So some of you females believe, well, I don't know if you don't believe in the equal, well, I don't believe in equal rights, maybe. In the context of that. But if it's equal rights, it means well, woman and man have equal say in the relationship. But fine. So that work, yes. But
Not in every case, sir.
all right. Where Jedari Masha Carter, Jedari and Benito. If you never say something well. Girl, them silent card that they love.
Yeah, girls, just
Eh?
true.
Yes, everybody. Right. Yeah, you know what? But I say a covalent bond with two same type of atoms is like equal rights. This is not equal rights here. Not at all. I tend to use relationships to explain bonding because I find out say it actually work. If we were to look at bonding, we could counsel people and relationships and show them what is what. The simple thing, if you not balance, if you not equally share things, then all right, you not have a certain type of relationship. If it's a case where one person dominate the relationship, then you're gonna have an unevenness. It can work with that way, if one person decides that them are going to yield into the person who's stronger and really not say nothing, can't bother them and just go and work with anything. You have that too. But then that's what like covalent bonds would be like. It's either one dominate or are on equally share, you know. Maybe the man earn more money than woman. Or what if it's two women? Who am I to discriminate there? Well, anyway, let's move on. The chlorine and the oxygen, as we say, when them react with hydrogen, they go bullet. Basically, I pull the electrons and make it polar. However, like let's say now, and okay, we're gone 3 minutes over time. But then let's have hydrogen here. Even carbon dioxide is slightly polar too. Don't forget this one. But then it's less polar than the water. But H2, N2. This one is very non-polar as well. CH4. And of course, NH3 is a little polar. So again, we went to talk more about this next slide, but then the reason we need to know this is that we can predict which covalent compounds will react with the or will be electrolysis with current be able to separate. The current couldn't separate hydrogen and nitrogen and this. Although current can separate nitrogen if you look at the nitrogen cycle with the role of lightning, but then lightning is a whole heap of current. So a different story though. But then certainly non-polar compounds, current can pass through them. Period. All right. So next class we'll learn some more about it. You guys have any questions?
No, sir.
No, sir.
All right. And so we could modify this definition to separate any compounds, or we could say, are polar covalent compounds into their constituent ions. All right. So water can be separated. Next class, we're going into details. What does water separate into? All right. So, so thanks for being here this evening, guys. I hope you learned something and hope you take up your book as well to make sure that what you learn doesn't leave you. All right. You have that responsibility to yourself. And I will try to send this information in the group. All right. So, all right, somebody text in the
Yes,
chat.
sir.
Let's see what them say here. Hold on. Gabby Davis Gabby was laughing out loud, man. what was funny, Gabby? Probably it might not work. All right.
Equal rights.
Oh, all right. You know what? I think I said too much. Might have offended Benito and Janari. So you know,
Terminate, you know.
it's nothing. Okay.
Yes.
Cool.
Yeah, you agree, sir, with me. You agree, man. Change your mind now.
Again. So when you bought in, we just there say girls, we just there say these are girls, a girls here talk. That's all. That's all.
Yo, you guys, you know, I really like you guys. You know, you guys are a good class. It's a pity we can't meet face to face, but I tell you, this helps. You know, we have to apply the thing to real life in order for it stick. If you not take up in a book, then carry the book to whatever you're taking up. So whatever it is you're not taking up, you know. So, but that's where you go, guys. Wish you all the best though. And have yourselves a wonderful evening.
Thank you, sir.
Yes, sir. Same to you, sir.
Yeah, man. All right. Let me just work on this. All right. Let's see something here. So that's cool.